Hello again, still May the 5th. Let's try to see how far I can come solving this problem before my afternoon coffee. This one I think I have solved. You see, this reminds me of the limit we apply when we use the sieve of Aristoteles to find prime numbers. I'll just show it. To find the primes less than or equal to 24, we first delete, or not 2 itself, but all the multiple of 2. And next we have 3 haven't been deleted, so we delete all the multiple of 3. And then we are finished. The numbers that remain are all primes. The reason we only need to go up to 3 is because the square root of 24 is less than 5. And that means that when we have a divisor of 24 larger than its square root, say 8, then the quotient 24 divided by 8 is 3. Then there'll be a divisor smaller than 3. Then 3 will be a divisor as well. That means that the number of divisors are limited by the square root, because to every one above there is one and only one below. So the square root of 24 is, now I'm mixing it up, but that should take care of the first inequality. Now the next one is more technical. It reminded me of the course I took while majoring in mathematics in classical number theory, where we did prove some equations along these lines for various functions like the Euler's totient function and so. Then while I was shifting the sheets on the bed, I've just done the laundry, I got the idea, or remembered, that we could try to take what are the number of divisors smaller, of all the numbers smaller than m. So sigma of m is simply the sum 1 to m of the number of divisors of n. So this is the number of divisors of all numbers smaller than m. And we can simply take, if we have some m here, up to m, that's silly, 1 up to m, then up to square root m, now what am I doing here? Well, if we take, I'll just show another thought. If we take like an I in here, then it divides I, 2I, etc. up to the integral part of m divided by I times I. This is the last one. So that means the number of numbers I is the divisor of is the integral part of m divided by I. And that must only go up to yes, how far must that go? Well, we must go up to m itself, because m is a divisor of itself. One occurs as a divisor of all the m numbers, 2, half of them, etc. So that was my idea, that we might get lucky after writing this up. The next thing is, could this in any way be used to say something about this? Then we should assume that for some numbers it was larger than epsilon. For a set of numbers this was larger than epsilon. Maybe we could write it in another way. Going up to m halves, there's only one. So from m halves, from 1 to m halves, all above that only divides m once. Now that's just doing the same another way, changing the sequence, you know. On the other hand, then down to m third. So here it only comes once, here it comes twice. Down to m fourth, it comes 3 times. So that's of the order of m12, that's m6. That's m halves. m third, m fourth. It actually comes down to the same. Let me make a table and then let's see if that gives any insight into it. I'll just pause the video while I make the table. Here we have the table, first the number of divisors, and then I've accumulated them. And from a certain step, it's capital sigma of m is larger than 2m. That's most obvious. Or should we say larger than equal? But then from 8 of, let's just say larger than m for m larger than equal to 8. Actually 6 will do. There's only one divisor of unity, and then that is offset here, and then primes have 2 divisors, so this equality holds. And that's of course equivalent to this, so there's no real insight there. I'm lacking an idea, so it's time for my coffee break. I just got an idea. Then we need to think a little how to bound it. It's bounded by the logarithm of m. So if we have like 1 divided by x here, and unity here, that's, never mind. Then this is equal to the, or this can be bounded by 1 plus ln x, ln m. This is really nice. So that was the creativity of it. How do we go back and say something about sigma naught from here? Let's try the other way and assume that we have a sequence of m's so that mi minus epsilon, that's the sigma of mi, are larger than some delta. I don't see the contradiction. Well, that was one step further. This idea was very efficient in creating a bound. It was a very good bound we got, but I can't make it give a bound on sigma naught itself. If we combine it with this, then we get that it's larger than m times 1 minus ln m. So there's a lot of space above m. Oh, but that might actually eat the. Let's just try that. I got the idea while drinking my coffee to take first a prime power and then a product of two primes, and then bound the number of divisors by the usual formula. But let's just look at this first. So this is m minus 2m. That is m ln m minus 2 plus 2 . So very much space. We actually have a bound that's larger than m to the first. Then we get some, m to the first. So that's a bad bound. So let's first take a prime factor. So that holds. Now it's if two primes and what can we do here? It's like we are down to the logarithm of n somewhere, somehow. This is smaller than log p1 of m plus 1. We'll probably skip that, times log p2 of n We might be onto something here. I can't combine the epsilons because there's a variable number of factors. So if we should have an n of epsilon on here, then we take n to the halves and this tends to naught as n tends to infinity. But when we have potentially an unbounded number of prime divisors, then we can't from this alone conclude that it holds for everything. But the idea seems promising. I just have to be much more efficient here. We can actually split n into the prime factors. So we only take out the prime factors, the distinct prime factors. That's if there are 2. And what if there are 3? Oh yeah, then the product of the prime factors will give n. So we can just put out the prime factors here. I have to work on that idea. It does sound a little too complicated. But what I would try is to find a bound where this is smaller than any given delta, and then see that bound is independent. If I can find a bound independent of delta, no, independent on the number of prime factors of n. It sounds a little too complicated. Time for another break. Good morning. It's now the 15th of May, and it's not that I haven't been working on the problem, but I've been a week in Madrid on a lovely holiday. We wanted to experience warm weather and not the cold weather of Denmark where we live. That was very nice. I did work a little on the problem. I couldn't help myself. What I basically wanted was to see if I could use any of the theory of this section or even chapter to solve the problem here. And I did get an idea. It occurred, finally I was able to prove that the zeta function squared equals this. It's very simple to prove. The zeta function is this, and if we expand this and differentiate it, and then substitute x for p to minus s and multiply over all primes, then the left-hand side gets the zeta function squared, and the right-hand side is the product over all primes of 1 plus 2p to minus s plus 3p to minus 2s plus etc. And multiplying all this, because the number of divisors is multiplicative with mutual prime factors, we get exactly this. That means that this series converges absolutely when S, let's just say it's real, when S is larger than unity. But then I felt very much back to this. I couldn't prove that the sum tended to naught like uniformly. So it might be very rarely above a fixed number, like the squares, and then it would still converge. So I couldn't use this, but at least I was able to prove to myself that I can apply the theory we've had. So back to the question. I use mu instead of epsilon because I want to have epsilon here. That's the more standard notation for some positive epsilon. So I'll see if I can decide an m. So we prime factor m. This product must be smaller than epsilon. And that leads us, of course, to consider a function e plus 1 times p minus mu e, where e is an integer and this may be larger than unity for a while, and then it will tend to naught very quickly. At some point it will start being almost exponentially decreasing. And I believe that p equals 2 is the slower of them. So that is, if we take the primes, and e let's disregard. Let's disregard naught. Just take 1, 2, 3, 4. So each of these tend to naught. And I believe that 2 is the largest. As a function of p, it decreases, so they are all smaller than 2. Now we know that. Next, where is the maximal value? So this gives mu x minus 1, so we put that outside. Maybe that's silly. Well, never mind. And then 1, that gives p. Oh, that's nice. And then this gives I think this is wrong. Who knows? At least this is an increasing function of x, so from some point it will be decreasing. And then the value naught, the maximal value, p equals, I'll just write it up, so this is the maximal value. So that seems to be increasing with p. That was not what I expected. I'll just make a small break and control this. I expected the maximum value to tend, the maximum point to tend towards 0. Maybe I'm still in holiday mode. I had to check it with Mabel. We differentiate with respect to x here, so that gives mu times ln p x plus 1 equals p divided by mu ln p But this doesn't tend to naught as I thought. But it must when it becomes smaller. No, not necessarily. Let's check what Mabel says. Oh yes, I made that wrong as well. It's p to minus most embarrassing. I'll do that again. First we have p, as p tends to infinity, x will tend to minus 1. And that means that at some point the maximal value will be at e equals 1. So let's see what that maximal value is. No, it will be at naught, of course. But, well, that's unity. So let's just take f of 1, because it'll be below that. Which, of course, tends to naught. Now we come to my idea. And that's that we have some maximal value, and it's of course some integer. Let's just make it decrease slowly. And eventually this will be below any positive number we choose. And then the idea is to take the product of all of these. this is higher than any product these primes can give. So we call that n. I don't know how to put that. I'll put maximal E. Optimal E would have been better. And then as long as factor is larger than unity. So that's as bad as it can go. Then we need to find a number, a boundary out here so that if we have a factor, if we have prime 2, then e plus 1 times 2 minus mu e is smaller than 1 divided by n. And of course down here it's e, the maximal value is the value of e that gives the maximal factor is unity. So that's 2 times p minus mu is less than 1/n. So my claim is that as far as we are outside of this bound, that is, if the power of 2 is larger than whatever the bound is here, then the factor from 2 itself will be so small that whatever the factors here be, we are still home. And there are a lot of guys here that may come in that does, where it's less than 1, that doesn't matter. But as soon as we are out here where it's smaller than 1n, 1 divided by n. Now, is that really totally clear? Now this power of 2 won't do at all, because then probably the product out of all these guys being larger than unity will give an n lying out here. So I need to, but it's my idea to use this, but I still need a way to get to our boundary m. What I will do in the meantime is to try to make an example in Maple with mu being equal to 1/10, and let's just set epsilon to unity, or maybe if it's too trivial, 1/10 as well, we'll see. And then make this computation, find n, and see this boundary I was talking about, and then see if I can find a way to compute a boundary m, so that we are always so that there'll always be a factor outside this boundary. That's the last point I need. It's now the afternoon, still the 15th of May. I started going through the Maple, making the Maple script I said I would, defining the function where x is e, the power of p, and this is the condition, and differentiating, and etc. Then I realized that it's better to do it like this and find the maximal point for each prime, which is given here, and then the value of it is given by this, and I think as p tends to infinity, this will tend to infinity. Yes, that's true, but that's with p tending to naught, and p will be naught if the prime doesn't occur, otherwise unity. So that's not interesting really. And now I chose mu to be 1/10, and then all primes up to 2 to the 10th give a possible product to this function, to f. So it will have a maximal larger than the one we need. So we are getting some large numbers. Going back to the guy here, I finally found out how to do it. We need to find an m which is so large that either the power of 2 lie out here, or the power of 3 lie out here, or 5 or 7. If neither of those lie out here, then it must contain a prime so that this is fulfilled. That means that we must take the product of all of these prime powers where this holds, and then we are home. It actually exists, but let's just try to compute it. So we can't solve it in this loop. We found out that the maximal value was 2.8 to 10 to the 12th. So that's the product of all these values larger than unity. It was orders of magnitude higher than I expected. So now we can just forget m here. And then when we have that, we need to find out where each prime, for each prime, the value of, I'll just make a break and program it, and then I can better explain it. All right, I have done what I thought I would do. I don't know what I said. We take the multiplum. First we take the solutions to the function here, giving 1 divided by n, and we need the second solution. There's apparently always minus n or minus 1, and the second solution is the one we need, and then we compute the prime power and multiply all those, and then we get 2.41 times 10 to 24,500 almost. And now I claim that this is the capital M we can use, where it's easy to prove that it works. And the point being that if all of these primes have smaller power than what is needed to take this product to be below epsilon, then there will be a factor larger than, we just need to multiply by that, don't we? And then we are done. This was a very rough way of doing it, not at all elegant, but I think I've come through with it.